Yeah. Yeah. That kind of weirded me out a lot. Okay, so this is AP Chem Review, Thermodynamics.
Sequoia Holmes, please come to the K-Wing office. Sequoia Holmes, please come to the K-Wing office.
So with thermodynamics, probably the first thing you want to remember is that what's the difference between a state function and a non-state function? So state functions are path independent. And the state functions are delta H, delta S, delta G. And if you don't remember, H is enthalpy, which is a measure of heat in the reaction. Delta S is the measure of disorder in the system, and delta G is the Gibbs free energy. In other words, the amount of energy you have free to do work. Some sort of we can also add on here the energy of a system, and depending on the book you use, it might be delta E, or they might call it delta U, but they're the same thing. It's the total energy in the system. Non-state functions are path dependent, and that is Q and W. So when we calculate Q, we're typically using the equation mass times the change in heat times the specific heat. And for work, we're typically interested in pistons moving up and down in gases. So negative P, change in volume. And the pressure is going to be in kPa, because in order for work to be in joules, your answer to be in joules, a liter times a kPa is a joule. So your pressure will have to be in kPas. And your change in volume is final minus initial. Okay. The total energy change in the system is the addition of these two. So we would say the total energy change in a system is the change in heat plus the change in work. So depending on how you set up the experiment, Q and W can be different. That's why they're path dependent. But if you measure heat at constant pressure, we call that enthalpy. So delta H is measuring Q at constant pressure. So, I mean, it really, you know, they give them different names, but you really just want to think of delta H and Q as the same thing. They're measuring how much heat is given off of a reaction. If heat's given off, it's exothermic. Heat is absorbed, it's endothermic. Okay.
Just a reminder, there is a VAEA meeting that begins at 4 p.m. over at Badger Ridge in room 201. Again, a VAEA meeting beginning at 4 o'clock in room 201 over at Badger Ridge.
Delta S is the change in disorder in a system. And we want to go from order to disorder. And it's kind of the opposite of delta H in that we want delta S to be positive. That means you're going from order to disorder. And if you have a negative delta S, you're going from disorder to order. So we want to go to disorder. We don't want to go to order. And let's just see if I can get see if you can tell me what the delta S sign would be for something like
King,
this.
please call 4405.
That was a kid.
It was a really young teacher.
Really?
How about we take, I'm just gonna make up the reactions here. Balance this, we're gonna need a 2 here, 6 here, 3 there, and a 2 there. So, what's the delta S on this reaction going to be? It can be positive or negative. So, what has high order? Solids, liquids, or gases?
Solid.
Solids have high order. So, liquids have some order, not as much as solids. So we have 2 moles of solid, 6 moles of a liquid, going to 2 moles of an aqueous solution and 3 moles of a gas. So this side is going to be much more ordered because I've got a solid here in the liquid. This side, I've got a gas, is going to be much more disordered. So the delta S of this would be positive. What about, let's say, this reaction? Two moles of hydrogen gas plus 1 mole of oxygen gas going to 2 moles of water vapor gas.
Do you have to look up the delta S or not?
No, I can pretty much figure it out. How many things do we have, how many moles do we have on this side? 3. How many moles do we have on that side?
2.
3 things are combining to form 2. Is that becoming more disorganized or more organized? More organized. So delta S is going to be negative. Now, I purposely picked them all to be gases, right? Because that way, if it was, something like, up here, if this was not very common, but let's say that was a gas. 6 moles of gas and 2 moles of a solid, it becomes less clear as to what the answer would be. So typically when they give you a problem like that, it's going to be all one phase and you look at the mole ratio and like, oh, okay. Or you've got a lot of solids on one side and you know that solids are highly ordered. So anytime you break down a solid, that's going to be the case. So positive delta S, that's a good thing. Negative delta S, that's a bad thing. Positive delta H means you're endothermic. Negative delta H means you're exothermic. So this is, you want to be getting heat out, you don't want to have to put heat into it. So what happens if, you know, your delta S is negative, but your delta H is also negative? Who wins out? That's where you have the Gibbs free energy equation, which relates the two together. T is almost always, T is at 298 for our purposes. We're at standard conditions, so that's what the little circle means. The standard conditions is 25 degrees Celsius. If you change this temperature, you change these values, okay? But for AP Chem, they usually say, okay, you're changing the temperature, assume that the delta H's don't change, okay? Because in order to recalculate the new values, you have to know differential equations. So, but you don't. So if delta G is negative, what does that mean?
Reaction is spontaneous.
Yep, spontaneous. And if delta G is positive, then it means
No,
it's not spontaneous. Can I erase this top part? So when calculating delta H, the assumption is that the delta H information of all elements are 0 in their most common state. So anything like potassium solid, delta H information would be 0. Delta H information of chlorine gas would be 0. But the delta H information of monatomic chlorine gas would not be 0. Because the most common state of chlorine, the element chlorine, is diatomic. So if you change it to monatomic, something that's not very common, it's not going to be 0. And you have to look it up in the table. Okay, so elements in their most common states. If it was liquid chlorine, it would not be 0, okay, because it's not the most common state. And so you look up the delta H of formations, and you use that then to calculate how much heat is released in a reaction. So if I had a reaction like CH4 plus O2 balance it out. I'll need a 2 here. And I think that's good. No, I need a 3 halves here, because I need 3, no, I need a 2 there. So to find the amount of heat released from the reaction, you do the delta H of formations of the products minus the delta H of formations of the reactants. So you gotta look up those delta H of formations on the chart. And so that's kind of one of the problems they'll do, is they'll give you these 3 values in the chart, but not oxygen. But you know the value of delta H for oxygen, you know it's 0, because it's the element in its most common state. So that's how you do it. And it's basically the same thing for delta G. We would say the delta G of formation of elements is 0 as well. So if you want to find the amount of free energy reduced, given off by a reaction, you would do the same thing. find the delta G of formation of products minus the reactants. And you multiply them by their molar ratios. So whatever the delta H of formation of water is, multiply it by 2. And make sure you're using the correct water, whether it's liquid or gas, because they have different values. Okay. Let's see. That's pretty much it for chapter 6. Do you have any questions?
Is there, one where you do reactants minus products, or am I making that up?
No, there isn't one where you do reactants minus
Okay,
products.
because for some reason I
But
thought-
there is something kind of related. So let me show you that real quick. These problems are really long, so I will try to formulate one that's really short.
Aren't these like the bonds?
Yes, so suppose I want to find, like, let's pick this reaction. It's a easy one. Okay, so if I wanted to find the heat given off by this reaction, I would do the products minus the reactants. I first have to find the delta H of formations. So this one's 0, this one's 0. Then you look that one up, and the value for H2O liquid is negative 286. So if I'm doing products minus reactants, I would go, okay, the amount of heat released in this reaction is 2 times negative 286 minus 0 times 2, because there's 2 moles of hydrogen, plus 0. Products minus reactants. The other way you could find the delta H of this reaction is to look at the bond enthalpies. So this method is longer because you have to calculate the energy it takes to break all the bonds, and then subtract the energy it takes to form the bonds. So it's broken minus formed. Okay, so I think of broken minus formed, and I always say, since this process is a lot longer, I call this method a bunch of BF, broken minus formed. So, like if you have hydrogen, it's a single bond, there's 2 of them. So you have to look up what's the bond strength of that hydrogen. Bond energies. So that's 432, so 2 times 432 plus my oxygen bond, it's a double, so bond enthalpy of that is 495. So you add that up and now subtract one of my bonds over here. I've got 1, 2 OH bonds. And I've got 2 of them. So what I really have is 4 HO bonds. And their enthalpy is
Last night, the screen door was unlocked.
467. So we do the broken minus the formed, you'll get the same answer, or pretty darn close. But it takes more time to like add up all the bonds, and so this way is the fast way, okay? And, you know, products minus reactants, you do the same thing for delta H and the same thing for delta G.
What are the units for delta H?
Delta H, that's a really good question to bring up. So for delta H and delta G, the units are kilojoules per mole. And for delta S, the units are joules per mole calorie. So delta S is in a different unit. So when you are doing the Gibbs free energy, you have to convert delta S into kilojoules. So you're going to divide it by 1,000 as opposed to delta H, which is already in kilojoules. And that's another good thing to you know, bring up. Can I erase this? So if we go back to that water reaction, and we said that the delta H of that reaction was going to be, I think it was a 2 times 286.
Negative 286.
Okay, so 2 times 286. That comes out to be negative 572 kilojoules per mole. Okay, per mole of what? So this number belongs to all 3 of these things. So the delta H of this reaction is negative 572 kilojoules for every 2 moles of hydrogen. And it's negative 572 kilojoules per 1 mole of oxygen. And it's negative 572 kilojoules for every 2 moles of water vapor. So if I were to say, if I were to give you a problem, how much energy is released by, let's just say, 20 grams of hydrogen? Well, they probably wouldn't give you a mass of hydrogen, they'd probably give you a pressure and a volume and have you calculate it with PV equals nRT. So, yeah, let's just do that, that'd be simple enough. So, no, let's just stick with grams. So 20 grams of hydrogen, you would go, okay, I've got 20 grams of hydrogen. Hydrogen weighs 2.20 grams, convert it to moles. And then this is where people mess up. For every 2 moles of hydrogen, I produce that amount of energy. Because this number on top doesn't change, the per mole part of the bottom does. So for every 2 moles of hydrogen, I get negative 572 kilojoules. And so that would say that if I had 20 grams of hydrogen, this is the amount of heat released. 5,636 kilojoules. That's the amount of heat released. So people forget that 2 mole part. If it was oxygen, it'd be per 1 mole. All right? chapter 7, so there are a couple big equations here in atomic theory, and E equals HF, and depending on how they do it, sometimes F is written as the Greek letter nu for frequency. So they're the same thing, frequency, and that's not velocity, that's the Greek letter nu for frequency. The units on frequency are reciprocal seconds, or 1/seconds. Another way you can write that is seconds to the inverse. And the other real big one is E equals hc over lambda. Lambda's wavelength in meters. So I think like when they ask you questions about like does something get bigger or smaller or increase or decrease, write the equation out. So if they have an equation that says, okay, what's the relationship between energy and frequency? If I decrease the frequency of my light, if I decrease the frequency of the light, what's going to happen to the energy of the light? It'll decrease. It's easy to answer when you look at the equation, right? If you decrease the frequency, the energy is going to decrease. Now they're not going to put the equation in the problem. They'll probably do something like somebody was trying to get electrons to jump out of a piece of metal. And when the researcher decreased the frequency of light, more electrons were emitted. What does that say about the strength of the light? So if you decrease the frequency, you decrease the energy. And what's the, when we talk about particles of light or packets of light, do you remember the name of that? Photons. So they'll say something like, what happens to the energy of the photon? And when they say photon, they're referring to light. So what happens to the energy of the photon if you decrease the wavelength?
Increases.
It increases, yeah. So if you decrease the wavelength, so things with really small wavelengths have lots of energy. And things with really high frequencies have lots of energy. I would memorize the 8 forms of light: gamma, X-ray, ultraviolet, visible, infrared, micro, radar, and radio. What's the speed of light?
3
3
times.
times 10 to the negative 8. So
Mr. Strauss, what's the one before radio?
radar. Boy, it's hard to say how in depth they'll go here. To calculate the energy of energy level, there's an equation for that. So you've got your nucleus, you've got your energy levels, and so to calculate the energy of an energy level, it's, you don't have to memorize this, you don't have to memorize it because it's there, but you just may not remember what it's for. 2.178 times 10 to the negative 18th joules over 1 over n squared. you've got, they might report it as z squared over n squared, but z is the charge on the nucleus. And you're always dealing with a hydrogen atom. So for the hydrogen atom, z is always 1. And so 1 squared is 1. N is the energy level. So the first energy level, you just plug that into your equation to find the energy. Now, if I were you, I'd go right away and multiply it by a mole, because that's usually what you have to end up to do anyhow. So if I were to calculate the energy level for the first energy level, I would plug in 1, I would multiply it by a mole, and I end up with negative 1310 kilojoules per mole. For the second energy level, I plug 2 in there, that's 2 squared is 4, so 1/4 of that times Avogadro's number. I get negative 327 kilojoules per mole. So if I want to find how much energy is released from an electron falling from this level to the next, I got 1 electron here that's falling. To find the energy released, I do the final minus initial. So negative 1310 minus negative 327 gives me the total energy change. So negative 1310 plus 327. So that's the energy that's released when the electron falls, okay? And I know some of this stuff is probably very obvious to you guys, but when an electron falls, it releases energy. And it releases energy in the form of light. So light will come out. Now how do I find that wavelength of light? Well, you know the energy, right? And you know this equation. Okay? Now, what's my energy in? Kilojoules per mole. Planck's constant. I've always reported Planck's constant 2 ways. 6.626 times 10 to the negative 34th joules per second per 1 particle. Or I've always just gone ahead and calculated the per mole part. You could have it as 3.99 times 10 to the negative 13th kilojoules per mole, or kilojoules second per mole. So if your energy is in kilojoules per mole, use the 3.99 times 10 to the negative 13th kilojoules times seconds per mole. I don't see this ever reported anywhere. I just calculated it because it's used so often. That way you're not, because how do you convert from this one to this one? Divide by 1,000 to convert it to kilojoules, and then multiply it by Avogadro's, or multiply it by Avogadro's. Okay, but sometimes it's just easier to have that written somewhere. So what happens when an electron jumps to a higher energy level? Is it energy absorbed or released?
Absorbed.
Or absorbed, right? So you can shoot light in to cause it to jump to a higher level. It must have exactly the right amount of energy to jump. If it doesn't have enough energy, it can't jump to the next level. Periodic trends. As you go down, radius gets bigger. As you go across the periodic table, they get smaller. So really, like an explanation, potassium versus cesium. Cesium's in the 6th energy level, potassium's in the 4th, cesium is going to be the bigger atom. If I compare cesium versus bismuth, they're both in the 6th energy level. But as you go across, the nucleus pulls the electrons in slightly. So every time you go one over on the row, you add one proton, you also add one electron, but that proton has the effect of slightly shrinking the atom. So cesium will be slightly bigger than bismuth, because bismuth has more protons, it'll shrink it. But dropping down a level has a huge effect, okay? So that's atomic radius. For the other trends, like ionization energy and electron affinity, you need to look at electron configuration first. So, like, they always like to ask exceptions. So, if you look at, as you go to the corner, ionization energy increases, as well as electron affinity. That's the trend. But they like to throw, like, exceptions to the trend at you. So explain why, or they might ask you to predict first, why does beryllium have a higher ionization energy than boron? Because here's beryllium, here's boron. So boron should have a higher ionization energy. But it doesn't. Beryllium's got a higher ionization energy. And with these two trends, the first thing you do want to look at is electron configuration. So if you don't remember how to do the orbital filling, you really should. Beryllium is helium 2s2. Boron is helium 2s2 2p1. So the first thing you want is a completely full energy level. So something like neon is helium with a 2s2 2p6. Second energy level is completely full. So it's got a really high ionization energy because everybody's paired up, everything's stable, it's good. It's not going to want to lose an electron. If you can't have a full energy level, go for a full sublevel. So having just the S level filled is going to be stable. So, 1 second. Hello. Yep. Where are you? Oh, and we're back. So, so a half-filled, like beryllium, is going to be more stable than boron, because boron would love to get rid of one electron to be like beryllium. Okay, and if you can't have a full sublevel, then you want to be something like nitrogen, which is half-filled. Okay? And if they ever ask you how many paired electrons are, Julia, don't be fooled.
Okay.
If you have something like this, they say, how many paired electrons do you have? You might go, oh, there's a pair, and I have one pair there, and so I should have one unpaired. Usually people get fooled by when they do something like that with oxygen. Because they say, oh, 1, 2, 3 pairs of electrons. No, you've got to do the orbital diagram because one in each house before you pair them up. So there's a pair, 2 unpaired. And typically you only look at the valence electrons. The valence electrons are all the S and P in the outermost level. Okay. So those are the ones you look at. And then it's basically the same thing with electron affinity. You look at the electron configuration first, and if they've got the same electron configuration, then you look at atomic radius. So like who's easier to ionize, sodium or cesium? Sodium is neon 3s1, and cesium is xenon 6s1.
Wait, are we talking about electron affinity or ionization?
Ionization.
Oh, okay.
This is going to be easier to remove because it's farther away. It's in the 6th energy level. Okay. But look at the electron configuration first. Do you need me to remind you how to fill the orbitals or no? Electron affinity, don't confuse it with electronegativity. Electron affinity is the amount of energy released when an electron is added in the gaseous state. So if I have regular old fluorine or monatomic fluorine in the gaseous state, and I add an electron to become this, how much energy is released? That's electron affinity. If we were dealing with sodium, it would have, or let's just pick a solid, a more common solid, like copper, it would have to be in the gaseous state. Now you can probably figure out just from looking at this, you know, the nonmetals, they like to form negative ions. So the nonmetals, they're going to release a lot of energy when you add an electron. Metals, they don't want to have a negative charge, so they're not going to release much energy at all.
So with the whole energy thing, like when it's ionization energy and like you'd say like it wants to lose an electron, then it'll be low ionization energy. But then when
You're talking about ionization energy?
Yeah, but then when you do electron affinity, it's high
so,
if it wants to.
if
Like
it
the
wants an,
energy
if
is
it
high
wants
if it
an,
wants to-
if it wants an
You know what I mean?
electron, if it wants an electron, it's going to release a lot of energy.
Yeah.
Okay. If it doesn't, for ionization energy,
If it
it's how
wants
much
to-
energy you have to put in to remove it.
If it wants to, so it's gonna be low. If it's like
If it's easy to remove.
if it's easy
If
to
it's
remove,
easy to
yeah.
remove,
Then it's
the
low,
amount
but
of energy you have to put in will be low.
Okay.
But then
yeah.
But
for
remember,
this
with
one-
all ionization
Yeah.
energies, and all ionization energies, they're all positive. You have to put in to remove an electron. Okay, doesn't matter which one it is on the periodic table. You got to put energy in to remove it. Whereas here, if I add this electron, I get
You'll
energy
get-
out.
You'll get energy. Okay.
Okay. Now there are some of them where you do have to put energy in, and they're basically there are two columns: the alkali earths and the noble gases. Because we said beryllium's stable, right? Well, beryllium does not want to do this. It really does not want to do that. So that delta H for the alkali earths are positive. Same thing for the noble gases. It really does not want to do it.
Okay.
But yeah, it does get a little confusing. And electronegativity is different because electronegativity is how much you attract an electron to yourself when in a bond. It's kind of like who can pull the electrons to themselves with greater strength. So if you have, let's say, carbon-hydrogen bond. No, let's do carbon-oxygen. A carbon-oxygen bond. Just trying to find the values here. 352. So like carbon is 2.5 and oxygen's 3.5. You got a shared pair of electrons in there. The oxygen is going to pull the electrons closer to it. Okay, so it's not like here electron affinity is okay. How much does that monatomic oxygen want an extra electron? That's electron affinity. This is electronegativity.
Is that what causes a dipole?
So for electronegativity, that's what we use to figure out whether something's got a dipole. or
Okay.
not. So if the difference is greater than, usually, if it's greater than greater than 0.4, we say you are a polar covalent bond.
If it's,
Oh, I'm sorry. You were no, that's not. It's usually not how you determine whether something's got a dipole. Okay. So if it's greater than 0.4, it's a polar covalent bond. Okay. But it doesn't tell you whether or not your molecule is polar. So don't confuse polar bonds with polar molecules. And I'll give you an example here. So here's carbon dioxide. Carbon's 2.5, oxygen's 3.5. It's a covalent bond. It's a polar covalent bond, in fact. So you got two polar covalent bonds here. But what's the symmetry of this molecule? Is it asymmetrical? No, it's symmetrical. So this thing is symmetrical. So the overall shape of the molecule is symmetrical. And if the molecule is symmetrical, then it's a nonpolar molecule and would have van der Waals forces. If I change this to be carbonate, can I do that? Yeah. Carbonate, there's 3 oxygens coming off of it. It's got a 2- charge. There's a lone pair of electrons there and a resonating double bond. Does it? Maybe not. Does not. How about we do? Carbonate doesn't work. But if I'll just do water. So water, what makes water a polar molecule is the fact that it's asymmetrical, the molecule itself. So you can have polar bonds, but be a nonpolar molecule. The only time where electronegativity is used to determine the polarity of the molecule is if your molecule only has two atoms. Because if you have two atoms, you're automatically linear. So you're automatically symmetrical. So only when you have two atoms do you look at the electronegativity. Like for example, HCl. So H is here, Cl is here, 2.1 to 3.0. You do the subtraction, it's 0.9. So it's a polar covalent bond. So what does that mean about the electrons in the middle here? They're being pulled towards the chlorine. So if I was going to draw my electron density, it looks something like this. Because all the electron densities pull over the chlorine. So this side of the molecule will be partially negative, this side of the molecule will be partially positive. And therefore HCl exhibits polar bonding. And that's why HCl dissolves in water. It's a polar molecule that dissolves in water. So that's the only time that you look to electronegativities is when you're dealing with just two atoms, because it's automatically symmetrical, so you gotta...
Wait, so if the electronegativity difference is greater than 0.4, it's
Polar covalent.
Okay.
Yep, and if it's only, and if the molecule's only two atoms big, then it's gonna be a polar molecule as well.
okay.
This line should go the little
Yeah.
like, then should go the other way. With
The little
the 0.4,
alligator
no, the
mouth
0.4
should go
in
the other way.
Yeah.
Yeah.
Is it the
Whoops.
bonds greater?
I hope the rest of you watch the video to the end. All right.
Should that
Let's
be
see.
a mistake?
I think
I mean,
it
it's outside school hours, so maybe it
still
should count for.
counts. Yeah, it counts.
Alright.
Let me just see if there's anything else in here that I really want to
Do
mention
you
as
guys
far as
catch his mistakes during first hour? Or
We tried.
they're
We
not
tried.
awake during first
you
hour.
guys are probably too polite.
Sometimes we mention them and you don't mark them.
Yeah.
You know what? I do mark them then later on.
Oh.
I seriously do.
Oh, sure.
I do. There are
Have
sometimes
you
where
ever thrown the party before? Like, yeah, no one wants you. They did? Well, when Chem,
He had me for a minute. Okay, his name is 2000.
you should just throw the party because we're a good class.
you are a very good class.
What would you do if we didn't show
Oh.
up to class after the AP test?
I mark you absent.
What are we gonna do in class that day?
We will do something. in
You
class
won't be
that
in
day.
that, but like,
But you're
the
not going to
AP
be here.
test will
the
go
AP
till like
test.
5th hour. You're excused
Yeah.
through 5th hour.
Oh, okay, never mind.
But one last thing and then we'll be done. Pi bonds and I'll do this quick. So remember, double bond is when you have sp2 hybridization and you're going to have one single bond and one pi. If you got a triple bond, you've got sp hybridization, one sigma, and two pi's. Okay? So the exception to this is if you have two double bonds in a row. That's the same thing as a triple. So if I had this molecule, okay, and I asked you to tell me the hybridization on each of the carbons. So that's a double bond, right? That's sp2 hybridization. That carbon's got a double bond, sp2 hybridization. That carbon's got a triple bond, sp hybridization. That carbon's got a triple bond, sp hybridization. What about that guy,
SP3.
sp3? how many pi bonds are in this molecule? Well, there's one pi bond from that double bond, and there's two pi bonds from this one. So that gives me 3 pi bonds. How many sigma bonds? Every single bond is 1 sigma. So that'd be 1, 2, 3, 4, 5, 6, because I have 1 in that double bond there, right? 7, 8, 9, 10. So 3 pi bonds and 10 sigma bonds, okay? Like I said, the only exception is if you have 2 carbons in a row, 2 double bonds in a row. So if you had this carbon is sp2. And you can also think about it as how many things are coming off of it. 1, 2, 3. So that carbon's sp2 hybridization. That carbon's sp2 hybridization. But that carbon there, 2 double bonds in a row, is equal to a triple. So that one is going to be sp. And again, you could also think of it as how many things are coming off of it. 1, 2. I'll have a pi bond here and 1 pi bond there. So 1 pi, 1 pi. So I have 2 pi bonds in that whole molecule. All right, I think that's good.